Teleportation has long been at the intersection of science and science fiction, inspiring both rigorous scientific inquiry and imaginative speculation. In today's discussion, we delve into the technical foundations of teleportation, exploring its theoretical underpinnings, advanced experimental techniques, and the quantum phenomena that make the concept plausible. Our exploration will focus on the scientific realities that govern teleportation, rather than simply indulging in fantastical scenarios. We begin by examining historical perspectives and key conceptual developments that led experts to consider teleportation as more than mere fantasy. Adding depth to the conversation, we incorporate insights from high-level quantum mechanics, relativity, and information theory. Through a comprehensive overview of established experiments and recent breakthroughs, we shed light on the intricate processes whereby quantum states are transferred and reassembled. This session is specially tailored for those well-versed in physics and information sciences, aiming to provide a rigorous discussion enriched with data, technical details, and nuanced analysis. As we traverse through decades of scientific evolution, we maintain a relaxed yet precise tone to engage both experts and curious enthusiasts interested in the frontiers of modern science. Our journey into teleportation begins now. Let us now embark on this exceptionally detailed scientific investigation together. Indeed, historically, the notion of teleportation can be traced back to ancient myths and folklore, where mysterious forces allowed individuals to vanish and reappear elsewhere. Early references in literature and mythology celebrated miraculous transport, symbolizing transcendence of physical boundaries. Over time, these stories evolved into more structured science fiction narratives, where the imagination of writers began to flirt with the ideas of matter disassembly and reassembly on demand. Concepts of instant travel grew in popularity during the early 20th century, with the advent of new scientific discoveries and the exploration of electromagnetic theories. As scientific inquiry progressed, theoretical frameworks emerged aiming to describe such phenomena within the boundaries of physics. Pioneers in quantum mechanics and relativity began to question the limitations of classical transport mechanisms, exploring ideas that eventually paved the way for quantum teleportation. Researchers like Einstein, Podolsky, and Rosen probed the implications of quantum entanglement, which hinted at the possibility that two particles could share information instantaneously, regardless of distance. These foundational experiments and theories provided a fertile ground for later advances. In subsequent decades, experiments with subatomic particles further refined our understanding of quantum states, leading to greater scrutiny of how information could be transmitted without violating the speed of light constraint. The transition from metaphysical speculation to rigorous scientific exploration marked a significant evolution. Researchers started embracing sophisticated mathematical models that merged quantum theory with electromagnetic principles. This shift was instrumental in moving the conversation from pure theory to experimentally testable predictions. Today, historians and physicists alike recognize that early conceptualizations, though steeped in myth and imaginative literature, have influenced the pursuit and characterization of teleportation within modern science. By tracing these conceptual roots, we appreciate how interdisciplinary influences, from literature, philosophy, and emerging physical theories, contributed to a paradigm shift. Moreover, understanding this evolution helps frame the ongoing debates about the feasibility and future of teleportation in a world governed by quantum laws. These historical insights not only illustrate the evolution of scientific thought, but also emphasize how interdisciplinary approaches have bridged ancient myths and cutting-edge quantum experiments. This transformative journey from fantastical lore to rigorous physics demonstrates that even the wildest ideas can inspire groundbreaking research. Each advancement paves the way for deeper understanding and further technological breakthroughs, fueling both academic inquiry and practical innovation in the field of teleportation research. By connecting historical narratives with modern experimental achievements, scientists continue to redefine the boundaries of possibility. In the realm of physics, teleportation is examined through the lens of both classical energy conservation and quantum information theory. At its core, rigorous analysis begins with Einstein's theory of relativity, which imposes a strict speed limit for any exchange of information. This theory underpins our understanding of causality and forbids any instantaneous transportation of matter, thus directing scientists to explore alternative explanations that comply with relativistic principles. A fundamental concept is that information, rather than matter itself, is the primary quantity to be transferred. Quantum mechanics introduces a more nuanced perspective. The peculiar properties of matter at microscopic scales, such as wave-particle duality and inherent uncertainties, have provided fresh possibilities to reinterpret teleportation. Concepts like quantum superposition suggest that particles may exist in multiple states simultaneously until observed, and quantum entanglement shows that two particles can be intimately connected regardless of their spatial separation. This entanglement forms the backbone of quantum teleportation experiments that rely on the precise encoding and decoding of quantum states. In this context, information theory plays a crucial role in defining how data about quantum states is transmitted. Digital encoding, combined with statistically robust error-correcting codes, ensures that the integrity of quantum information is maintained during the transfer process. Experimental protocols often utilize Bell state measurements and quantum channels to achieve successful state reconstruction. It is noteworthy that while the term teleportation might evoke images of instantaneous human transfer, the actual scientific process involves the accurate replication of state information using pre-established entangled pairs. Additionally, researchers apply advanced mathematical models to quantify the efficiency and limitations of teleportation protocols. Statistical analysis and probability theory are employed to predict error rates and fidelity outcomes in experimental setups. The energy requirements, though substantial for large-scale teleportation, are scrutinized through both thermodynamic and quantum mechanical frameworks that reveal elegant symmetries and constraints. Differential equations and tensor calculus further support the development of theoretical predictions that guide experimental designs. As research continues, these analytical techniques are refined, bridging the gap between abstract theories and tangible technologies. The synergy between physics and information theory has opened new avenues to test the limits of data transfer over quantum networks, with each experiment contributing to a richer understanding of fundamental phenomena. The rigorous integration of theoretical models with scalable technological applications drives the field forward, as scientists endeavor to achieve ever higher fidelities in state transmission while adhering to the immutable laws of nature. The collective framework of physics and information theory not only demystifies the process of teleportation, but also sets stringent benchmarks for experimental replication. Researchers meticulously calibrate quantum channels and optimize entanglement distribution protocols to secure near-perfect fidelity. By leveraging a confluence of theoretical predictions and real-world testing, scientists are gradually overcoming obstacles that once seemed insurmountable. This convergence of disciplines reinforces the notion that even highly abstract ideas must be validated through concrete mathematical and physical evidence, thereby strengthening our confidence in both the principles and potential applications of teleportation. These efforts steadily chart new territories in quantum physics. Quantum teleportation refers to the process by which the state of a quantum system is transported from one location to another without any physical transfer of the system itself. Far from the dramatized depictions in popular media, this protocol relies on the phenomenon of quantum entanglement and the precise measurement of quantum states. In practice, an unknown quantum state is measured along with one component of an entangled pair, and the measurement results are sent via classical communication channels. The recipient uses these outcomes to perform specific operations on the second entangled particle, thereby recreating the original state. This protocol ensures that no information travels faster than light, adhering to the fundamental limitations imposed by special relativity. At the heart of quantum teleportation is the Einstein-Podolsky-Rosen paradox, which questioned the completeness of quantum mechanics and led to further investigations into the nature of reality. Bell's theorem and subsequent experiments have validated the non-local characteristics of quantum entanglement, confirming that measurements performed on entangled particles can instantaneously affect one another. These principles underpin a series of protocols, including the famed Bennett-Brassard protocol, which laid the groundwork for transferring quantum information over short distances with high fidelity. In recent years, advances in photonics and superconducting qubits have enhanced our ability to control quantum states experimentally. Researchers employ state-of-the-art techniques such as dynamic decoupling, error correction, and quantum repeaters to mitigate decoherence and losses during the teleportation process. Detailed mathematical formulations, including density matrix representations and block sphere visualizations, help clarify complex operations such as unitary transformations and entanglement swapping. The precision of these measurements is often verified through statistical analyses and quantum tomography, which collectively map the fidelity of quantum state reconstruction. Emerging experimental setups now demonstrate teleportation over progressively longer distances, paving the way for robust quantum communication networks. Theoretical models incorporate sophisticated quantum circuits and Hamiltonian dynamics to predict performance metrics under varying environmental conditions. This blend of theory and practice not only enhances our comprehension of quantum state dynamics, but also serves as a critical stepping stone toward practical quantum computing and secure communications protocols. Looking forward, the continuous refinement in controlling quantum systems promises even more reliable teleportation mechanisms. As experimental error rates decline and technical challenges are addressed, researchers are able to implement innovative protocols that improve fidelity and efficiency. The integration of quantum error correction methods with high-quality qubit control fosters progress in both theoretical and experimental arenas. This concerted drive toward enhanced teleportation underlines the potential of quantum technologies to transform communication infrastructures in the coming decades. Ultimately, quantum teleportation embodies a harmonious blend of theoretical sophistication and experimental ingenuity. Each protocol refines our capability to manipulate quantum states with unprecedented accuracy. As we push the boundaries of what is experimentally feasible, the foundations laid by early pioneers continue to inspire contemporary innovations. This relentless pursuit of excellence in quantum state transfer marks a significant milestone in the ongoing evolution of quantum technologies. Indeed, crucial. Experimental breakthroughs in the field of teleportation have steadily transitioned theory into practice. Over the past few decades, breakthroughs in quantum optics, superconducting circuits, and ion traps have contributed to a series of high-fidelity teleportation experiments. Researchers have successfully demonstrated the transfer of quantum states between photons, electrons, and even complex atomic ensembles. These experiments typically involve creating entangled pairs, performing Bell state measurements, and using classical communication links to complete the teleportation protocol. The precision of these experiments is reflected in the increasingly high fidelities reported, some exceeding 90% under controlled laboratory conditions. One landmark experiment achieved quantum teleportation over metropolitan-scale distances using optical fibers, proving that quantum communication networks are feasible in real-world environments. In another significant development, researchers have implemented quantum teleportation protocols on solid-state systems, such as superconducting qubits and semiconductor quantum dots. These experiments have provided critical data on decoherence times, error rates, and the viability of integrating teleportation processes into scalable quantum computing architectures. Notably, the use of ultrafast laser pulses and cryogenic environments has minimized thermal noise and improved stability in these protocols. Recent studies have also explored hybrid systems that combine different types of quantum hardware. This interdisciplinary approach has allowed scientists to exploit the unique advantages of each system, such as the long coherence times of trapped ions and the rapid processing capabilities of superconducting circuits. Researchers now utilize advanced synchronization techniques and precise timing controls to coordinate complex experimental setups across multiple platforms. These improvements have opened avenues for constructing quantum repeaters, which are essential for extending the range of quantum networks and achieving global-scale quantum communication. Cutting-edge laboratories around the world continue to push the envelope with innovations in detector sensitivity and quantum control methods. By employing real-time feedback and machine learning algorithms, experimenters are optimizing operational parameters and dynamically adjusting experimental configurations to counteract environmental fluctuations. The integration of high-speed electronics with meticulously designed optical components has resulted in experiments that not only demonstrate quantum teleportation, but also test its limits under rigorous conditions. Looking ahead, experimental research is moving toward integrating quantum teleportation into practical applications such as secure communications and distributed quantum computing. Collaborative efforts between theoretical physicists, engineers, and computer scientists are accelerating the development of hybrid quantum networks. These networks promise to revolutionize data security and processing speeds by leveraging the intrinsic properties of quantum entanglement. The rapid pace of experimental innovation offers a glimpse into a future where quantum teleportation evolves from a challenging laboratory phenomenon into a cornerstone of advanced technological infrastructure. Recent innovations continue to transform our experimental landscape in quantum teleportation. State-of-the-art laboratories utilize innovative photon detectors, ultra-coherent qubit systems, and optimized feedback loops to achieve breakthroughs that challenge previous limits. These advancements provide deeper insights and enhance our ability to engineer robust quantum channels. As experiments become increasingly precise, the boundaries between theoretical concepts and practical applications narrow, paving the way for quantum networks that may one day redefine global communication standards. Despite significant advancements, numerous challenges impede the translation of teleportation from controlled experiments to everyday applications. One major challenge is maintaining quantum coherence over long distances, as environmental disturbances invariably introduce decoherence that diminishes fidelity. Error rates, even in meticulously isolated systems, remain a critical obstacle. Additionally, scaling experiments to accommodate larger systems or complex entanglement schemes is an ongoing technical hurdle. Researchers continue to innovate both hardware and error correction methodologies, yet the exponential resource requirements in many quantum protocols present substantial limitations. Another limitation stems from the fundamental nature of quantum measurements. The no-cloning theorem prohibits the creation of identical copies of unknown quantum states, complicating efforts to perfectly replicate information during teleportation. These constraints challenge the development of more efficient protocols and require increasingly sophisticated experimental techniques. In turn, the interplay between physical limitations and theoretical boundaries demands continual refinement of models and methods. Ethical considerations also emerge as teleportation technology progresses. Issues surrounding privacy, data security, and the potential for disruptive applications in military or surveillance domains require careful analysis. The prospect of transferring quantum information raises important questions about identity, consent, and the ownership of information in a highly interconnected quantum network. Regulatory frameworks and ethical guidelines must evolve in parallel with technological advances to ensure that the applications of teleportation benefit society without compromising individual rights. Furthermore, these debates highlight the need for interdisciplinary collaboration, where ethicists, policymakers, and scientists work jointly to navigate the ramifications of emerging quantum technologies. In addition to technical challenges and ethical dilemmas, addressing public misconceptions remains essential. Clear communication, transparent methodologies, and robust oversight can build trust. As the field evolves, aligning scientific ambitions with societal values is imperative for the responsible advancement of teleportation technology. Collaboration and innovation remain key to overcoming these multifaceted challenges, indeed crucial. Reflecting on the interplay between science fiction and current scientific progress, the future of teleportation appears both promising and complex. Advanced quantum experiments continue to challenge preconceived limits, transforming imaginative concepts into rigorous research endeavors. While popular culture portrays teleportation as an instantaneous, almost magical process, the reality is rooted in precise quantum state replication, governed by well-established physical laws. Future advances may extend the distances over which quantum states can be faithfully transmitted and might integrate seamlessly with emerging quantum network infrastructures. Overcoming persistent technical limitations will require innovative approaches to error correction, entanglement distribution, and decoherence management. Moreover, as ethical, legal, and societal considerations evolve, a balanced framework will be essential to ensure responsible deployment. Ultimately, the journey from imaginative speculation to demonstrable high-fidelity quantum teleportation embodies the transformative potential of interdisciplinary science, charting a course where visionary ideas inform practical applications.